Hello, my name is Jason Nikoff, and I'm a professor of agronomy and soil science at Tennessee State University. I'm going to be talking about weather for my drone certification training, also known as the Part 107 certification. So to start off with weather, we're going to talk a little bit about air density. And so in general, air density, as it increases, performance of the drone or the plane is going to increase and vice versa. Now, density is affected by altitude, temperature, and humidity. And so we'll delve into this a little bit more on the next slide. So density altitude is defined as the altitude in the standard atmosphere corresponding to a particular value of air density. And so there's a couple of vocabulary words where we talk about high density altitude. And so I usually think about high altitudes when we're talking about this. So in this case, we've got thin air, and this can be caused by high elevations, low pressure, high temperatures, or high humidity. And then low density altitude is the opposite. It can be caused by low elevations, high pressure, low temperatures, and low humidity. And so I mentioned that the density is going to be affected by a number of different factors. The first one that we've got here is altitude. And so as altitude increases, there's less air above pushing down, and gravity has less effect, which decreases the overall density of the air. And so as the air becomes less dense, then more thrust is required to make the same mass of air or to move the same mass of air over the wing. And so if we think about that as the density decreases, there's not as much. Think of air as being made up of a lot of different molecules, and so those molecules are going to push up against the front of that airfoil on the wing, and it's going to help to create that lift. And so as there's less density in the air, that's going to reduce that effectiveness. Now, increasing pressure is going to increase density. And so if you think again about the molecules in the air getting pressed together, there's essentially going to be more of them. And so that's going to help to push against that airfoil and create lift with that wing. And also increasing temperature is going to decrease density. And so temperature is really just another way of talking about the kinetic motion of the molecules that are in the air. So if the temperature's higher, the molecules are moving a lot faster, which essentially means they're spread out. Okay, so in any given volume of air, there's just not going to be the same mass of molecules there. And so if you look at the equation on the right-hand side, if mass decreases, then density is also going to decrease. And then the last one, as humidity increases, density is going to decrease. And so what happens here is in a given volume of air, you're going to have all different kinds of molecules. You're going to have nitrogen, oxygen, carbon dioxide. And so if you add more water, H2O, into that area, essentially what it's going to do is it's going to kick out a lot of other molecules. So it's going to kick out the oxygen and nitrogen and carbon dioxide. And the humidity or the water molecule is a lot lower mass molecule than nitrogen, oxygen, carbon dioxide. And so the overall mass of molecules that are there decreases. And so again, if you look at that density equation, as mass decreases, density is also going to decrease. Now we've got some atmospheric hazards. Of course, storms are a large one. And so normally a decrease in pressure is going to indicate that you're going to have a storm or some kind of bad weather. And that pressure is measured in inches of mercury. And the sea level pressure under normal conditions is 29.92 inches of mercury. So that's a good one to remember. And it's also important to remember that as the altitude increases, the pressure is going to decrease. So for every 1,000 feet of altitude, you're going to decrease the pressure by 1 inch of mercury. Now, we also have obstructions, which can create their own atmospheric hazards. So things like buildings or mountains. And so these are very similar to what we talked about in a previous module when we talked about turbulence on the aircraft caused by the wing and the angle of attack. And so this is the same sort of setup where we've got wind going up the mountain peak, and then as it comes down, it can't follow along that surface anymore because it's such a large angle that it creates that turbulence that we talked about on the wing of the plane. So that creates turbulence, and of course, when you hit turbulence, that can cause some atmospheric hazards. And then low-level wind shear. This is essentially a drastic change in wind speed, and it's called low level because it takes place at low altitudes. And a lot of times this wind shear is undetected. You can't necessarily see it. And so that's why it's always a good idea to, keep your situational awareness so that you're keeping a watch on things that just literally might come out of nowhere. Okay, the stability or atmospheric stability is essentially the atmosphere's ability to resist vertical movement. And so that vertical movement is going to create the instability. And so cool, dry air is going to be more stable than warm, moist air. And so the warm air will rise and it'll cool as it rises. And once it reaches an altitude that has the same temperature, it's going to stop rising. Now, when you've got moisture in that warm air, what it does is it slows down the air's ability to change temperature. And so that pocket of air that's warm and moist is going to shoot up faster and longer because it takes longer for that temperature change to occur. And so that's why warm, moist air is the most unstable type of air. Now, you can also have inversion layers, and this is a situation where cold air is found at lower altitudes and warm air is found at higher altitudes. And a lot of times this can occur on a clear, cool night closer to the surface, or it can occur when a front of warm air spreads over a layer of cooler air. And so the cooler air is where it wants to be, the warm air is where it wants to be, and so nothing really moves vertically. Now with dew point, when the air temperature decreases to the dew point temperature, then that's when we get moisture condensation. And so it can, we can see it as fog or dew or frost, rain, snow, clouds, a whole lot of different options there. And so dew point is the temperature at which a certain volume of air becomes saturated. And so on calm, cool, clear nights, where we have temperatures that drop below the dew point, we'll get dew formation. And then if the temperature is below freezing, then instead of dew, we'll have frost formation. And frost, of course, is really important on an airplane because that can increase drag, and it can also reduce the lift force by disrupting the flow of air over the wing. So those are some things to keep in mind for the exam as well. And then when it comes to clouds, all drone pilots are required to stay 500 feet below any clouds or any sort of ceiling. And so broken or overcast clouds are considered a ceiling. And so we'll talk about that a little bit later about how that classification works. Lenticular clouds, so those are the lenticular clouds that are shown in that image above the mountain there. Essentially, they have smooth, polished edges and are an indication of high winds and turbulence. Then we've got cumulonimbus clouds, and these are, of course, an indicator of thunderstorms and extremely turbulent conditions. And then the ceiling, like I said before, that's the lowest layer of clouds reported as broken or overcast. And so, like I said, we'll talk about that a little bit more on the next few slides, how we classify broken or overcast type clouds. Now, stable air is going to include the following characteristics. We're going to have stratiform clouds. And so you can see an example of those there. Stratiform clouds are essentially when you've got kind of a gray day. You can't really see the individual cloud formations, but the whole sky is just kind of gray. Those are the stratiform clouds. Stable air is also going to have continuous precipitation. It's going to have smooth air and poor visibility. So if you think about it, stable air is not moving, and so you're not going to be blowing, things out of the way, and so that visibility is going to stay there. Now, when we've got unstable air, that's usually defined by cumuliform clouds, and so with these clouds, you can see their definition, their shape. Unstable air is also going to be characterized by showery precipitation, by turbulent air, and good visibility. And so fronts are the area where two different air masses meet. There can be rapid changes of temperature, humidity, and wind across these zones. And then we've got warm fronts and cold fronts. And so warm fronts are going to be warm air. They're going to initially bring rain followed by clear skies, whereas a cold front obviously has cold air, and they can bring more torrential rains and high wind speeds. Now we've got a few other types of fronts. We've got a stationary front, which occurs when a cold and a warm front meet, but neither one moves out of the way, and they can bring long rainy periods. And then we've got an occluded front, and in this case, a cold front catches up to a warm front, and they can usually bring dry air. Then we've got high pressure and low pressure systems. A high pressure system is usually cooler and drier than the surrounding air and provides fair weather, whereas a low pressure system is usually warmer and wetter. And we said before, warm, wet air is going to be more unstable. And so we're going to see more storms and bad weather in those kinds of conditions. And then air is always going to tend to flow from areas of high pressure to low pressure. Now, you also need to know some information about a thunderstorm life cycle. If we're operating a drone, we're not going to be operating in a thunderstorm, but it's something that we still need to know for the exam. So essentially, there are 3 stages involved in a thunderstorm life cycle. You've got the cumulus stage, the mature stage, and the dissipating stage. In the cumulus stage, we've got where we've got the soil that's heated up from the sun. We've got a lot of these warm updrafts, and these warm updrafts continue to climb and to increase, and the air essentially becomes more moist and cools as it rises. And at a certain point, those thermal updrafts can no longer support the moisture, and rain begins to fall. And so once the rain begins to fall, we enter the mature stage. And in this case, we have the rainfall, which creates a cold downdraft. And so that's starting to cool the soil. And so over time, that's cooling the soil, and we're reducing these thermal warmer updrafts that we've had before. And so over time, once that soil is totally cool and there's no more thermal updrafts of warm air, then we enter the dissipating phase. And in the dissipating phase, the ground has been cooled by precipitation, and so there's no more thermal updrafts. And then, even the precipitation is starting to kind of slow down. Now, with the mature stage, that's the height of the thunderstorm. That's where you're going to have a lot of vertical shear, turbulence, and of course, you're going to see a sharp decrease in pressure, a sharp decrease in temperature, and a sharp increase in pressure. Now, there are some different reports that that airports and pilots use to identify different types of conditions. So the METAR is what's used to identify the current conditions at an airport. And you can identify those. There's a website that you can identify the METAR for different airports, and it looks something like this. So it's kind of a code that has to be decoded to be able to figure out what it's talking about and what it means. And so, of course, this is, an important part of the exam to be able to understand how to figure these out. So that's what we're going to do. We're going to start off and break it up into little pieces here. And so I'll go through each one and what they mean. So the first section here is the reporting station. So I took this from the Nashville airport, which is BNA. And so KBNA relates to the Nashville airport that the report is for. And then the next section is this 2-digit number, which is the day of the month that this report was pulled. And then the next section is the time. And so this is in Zulu time, or Greenwich Mean Time, or Universal Time Coordinated. Those are all the same meaning. And so you can convert that to Central Time or Eastern Standard Time. To convert Zulu time to Central Time, you're going to subtract 6 hours. And so 2053 will become 1453. And so then you can convert 1453 to 12-hour time. And so 1453 then becomes 2:53 in the afternoon. To convert to Eastern time, you would essentially subtract 5 hours instead of 6 hours, and then do the same types of conversions. Now, the next section is looking at the direction that the wind is coming from in degrees. And so I've got, this circle here just kind of depicting the different directions and their representation in degrees. And so you can see 160 would be somewhere between east and south, that the direction of the wind is coming from. And then the next section is going to be the speed of that wind in knots. So in this case, we're looking at 4 knots. The next section is going to be the visibility. So this is the visibility is 10 statute miles. And so this is a good area for identifying the visibility to know if you can fly. So if you remember, the regulations required you to have at least 3 miles of visibility. So this is where you can find it for sure to know, that you've got at least 3 miles of visibility. The next section are focused on the weather conditions and the sky conditions. So in this case, SKC means clear skies. And so we've got a number of different designations that we can have for this, depending upon whether they're thunderstorms or snow or fog and those kinds of things. So this is a good chart to kind of refer to and kind of study a little bit to know what some of those different abbreviations might mean. And so we'll also sometimes just to draw your attention to it, the plus is going to mean a heavy and the minus is going to mean light. So you might see some of those with your examples as well, or with the questions on the exam. So coming back to this, the next section are the sky conditions. And so in this case, this is where we can identify that ceiling. I talked about the overcast and broken clouds are our ceiling. And if you remember, we have to stay 500 feet below that. And so in this case, for this METAR, we've got overcast clouds at 3,400 feet. And so what we do is we just take the 34, the 034, and we can change that into the 3,400 feet. And that's in AGL. So that's above ground level. And then the next section is our temperature and dew point, and those are in degrees Celsius. So we've got 8 degrees Celsius for air temperature and 2 degrees Celsius for dew point temperature. And then this section is the altimeter reading, or the altimeter setting in inches of mercury. So it's 30.26 inches of mercury. And this allows manned aircraft to display the correct altitude. Despite changes in pressure, they can get a reading from the METAR at that specific airport. And then the last section are remarks. And so there may be some different types of remarks. This one in particular means that the METAR was generated by an automated station. And so that's essentially how you can decode some of these METAR statements. And so just one other thing I want to draw your attention to is the designation for the different sky conditions. So we talked about overcast, we talked about broken. We also can have scattered clouds, few clouds, and then essentially clear conditions, which are clear skies or few in some cases. So you can see overcast is designated as 8/8 of the sky is covered in clouds. Broken is between 5/8 and 7/8. Scattered is between 3/8 and 4/8. Few is between 1/8 and 2/8. And so you don't have to calculate the eighths or anything, but that's just important to know. So again, the ceiling is identified by the lowest layer of broken or overcast clouds. In our situation here, our ceiling is at 3,400 feet AGL. Okay, now we've also got these TAF, which are the forecasts. So the METAR were current conditions, and the TAF are forecasts for 5 miles around a particular airport. And so they have the same abbreviations as the METAR, but they also include time frames. And so this is an example of it. And so it's a little bit longer because it's broken up into different time frames that relate to the different forecasts that are there. And so if we go through it, so first off, the time frame here, the first time frame we've got is 11/12 and 12/12. So this means that it is valid from the 11th day of the month to the 12th day of the month, from 1200 Zulu to 1200 Zulu on each of those days. And so that's essentially a 24-hour forecast. And then it'll go and it'll break it up into individual forecasts. So tempo stands for temporarily or temporary. And so on the 11th day, between 1200 Zulu and 1400 Zulu, we will have these conditions. And so then if we move forward, we can see an FM, and FM stands for from. So then this is another section. So from 1500 hours Zulu, we'll have these next conditions. And then we get another FM. So from, and this is on the 12th day at essentially 2400 hours. we've got some new conditions. And this P, I want to note here, this P stands for greater than. So we didn't have that on the example before, but P in this case, so we're talking greater than 6 miles of visibility in this case. And then as we keep going forward, we've got some broken clouds, we've got some overcast clouds. So in this case, if we were looking for that ceiling, like I talked about before, our ceiling is going to be at 8,000 feet because that's the lowest level of either broken or overcast clouds. Next, we've got PROB, which means the probability of this situation is 30%. And then we've got another time indicator. So again, on the 12th of day of the month, from 2400 to 400 hours, we've got these conditions. And then again, from 400 hours on the 12th day, we've got another set of conditions. And then temporarily on the 12th day, from 400 hours to 800 hours, we've got another set of conditions. So you can see it kind of starts out with telling you what the forecast is for the time period, and then it breaks it up by individual time period. And so one last thing to mention are that there are a number of different systems that are used to identify the weather information or conditions at the airport. And so these are ATIS, which stands for Automated Terminal Information Service, or AWOS, which stands for Automated Weather Observing System, or ASOS, which means Automated Surface Observing System. And so when we go through the sectional charts module, we'll actually see some of these things on the sectional chart map, and that'll help us to identify it as a weather information service. So now there are a couple of maps that you'll have to kind of look at and answer some questions about on the exam. And so this is the first one. This is a weather depiction chart. And so the weather depiction chart shows different fronts that are across the map. It also shows different weather stations. Those are depicted as each of the different circles. And so the circles themselves look a little bit different. And so essentially a circle that's totally filled in, totally black, means that it's got overcast skies. If it's 3/4 full, or it's darkened 3/4, that means that there are broken clouds in that area. If it's 1/4 with a line down it, so there's a couple of these in Arizona, and so in that case, that indicates that we've got scattered cloud cover. And then if we've got one that's a 1/4 full, like we've got a few of these in Iowa here that are just a 1/4 full, then that means that they've got few clouds in that area. And then when we've got a fully white circle, that means that we've got clear skies in that location. Now, we've also got some numbers on some of these, and so that relates to the height of the ceiling. And so that is going to indicate, for instance, in Utah, we've got 70. And so that indicates that the ceiling is 7,000 feet. And that should be in AGL. And so also we've got some symbols at some of the weather, near some of the weather stations. We've also got some symbols. So we've got some that are maybe have 2 lines, some that have some dots, 2 dots or 3 dots or 4 dots. Some of them have some asterisks, and all of these mean different things. So if it's got 2 dots, it indicates that there's rain taking place at that location. If there are 2 commas or apostrophes, whichever you want to call it, then that means that there is a drizzle in that location. If there is a dot with a triangle, it means that it's a rain shower. If we have two stars or two asterisks, that means that we've got snow. If we've got a star or an asterisk with a triangle, that means a snow shower. Two lines indicate a mist, and three lines indicate a fog. So those are some of the most common types of different symbols. But you can look up, I think there's 100 total symbols, and that you can kind of Google and find them online and look at those if you want to. But like I said, these are the most common that you'll come across. Also, one other thing with the dots, the more dots that are there, that's going to signify basically a greater intensity or a heavier storm that's going to be there. Okay, now this is another one that is, well, actually, let me go back to this previous one. There is also an important thing, a legend that you want to make note of. And so in this legend, we've got some different things. We've got shaded areas are essentially going to mean IFR. IFR means instrument flight rules. So this means that conditions are so bad that pilots must rely on their instruments to fly. And so we have IFR with a ceiling less than 1,000 feet and or visibility less than 3 miles. And then in the areas that are surrounded by the contour lines, but they're not shaded, we have MVFR. So VFR means visual flight rules. So you can see there's no issues with being able to see out of the cockpit. MVFR is going to mean marginal visual flight rules. So in those areas, we've got marginal visual flight rules with a ceiling greater than or equal to 1,000 to less than or equal to 3,000 feet and or visibility greater than or equal to 3 to less than or equal to 5 miles. And then no contours, the areas without any contours means VFR. So that's visual flight rules. You can see out of the cockpit, no problems. With a ceiling greater than 3,000 feet and visibility greater than 5 miles. So that's an important piece to take note of as well, because that can help you with answering questions on the exam too. So this last chart that I've got here is a prognostic chart. So this focuses on some forecasting. And so the two charts on the left-hand side are going to be your 12-hour forecast, and you can see that in the legend on the lower left-hand corner. It says 12 HR. On the right-hand side, we've got 24-hour forecasts. And then the top two panels are going to indicate the weather more or less in the atmosphere, whereas the bottom two panels are going to be more focused on the surface conditions. So that's kind of how to look at those. And then the legend that you see in the very middle of the chart, that relates to the top two panels that are here. And so for the bottom two panels, the additional information that you'll need to know, of course, we've got some of the symbolism that I talked about on the previous slide. Also, we've got some colored lines. And so the green areas that are shaded with a green line around them, they mean that there is precipitation covering over 50% of that area. And then areas that are surrounded by a yellow line mean that precipitation is covering half the area or less. So that's another important factor to keep in mind to help you answer some of those questions. All right, so that finishes up weather. My contact information is here. If there are any questions, please feel free to reach out to me. The last and final module we have is going to be focused on those sectional charts.